So earlier we were looking at how the cutoff probability affects the performance of a model, and we were talking about what we can do about it. So one of the main techniques to select the correct kind of cutoff probability is what is called as an ROC chart, right? Earlier we spoke about how the cutoff probability is actually a trade-off. Now the notion or the idea of an ROC chart helps us to make this trade-off very, very explicit. So let's try and understand how to do that. Okay, so as I've already pointed out, the cutoff probability represents a trade-off. So in this case, with a 0.5 cutoff, you get a certain performance. With a 0.4 cutoff, you get a different performance, right? So with the 0.5 cutoff, we are being a little more strict about accepting somebody as a buyer. With a 0.4, we are being relatively loose. Obviously, this is going to identify more buyers, but at the cost of classifying more non-buyers also as buyers. Okay, so lower cutoff means more cases are classified as buyer. So we will identify more people who are actually buyers as buyers, but we'll also identify more people who are non-buyers as buyers. That's the trade-off that we are getting here. Okay, so here let's consider a test partition, and here is the actual class. So instead of saying buyer, non-buyer, etc., I'm just saying 0, 1. Okay, and these are the predictor attributes, income and age in this particular case. This is the actual class, the target attribute. And the success class, let's assume, is 1, right? Which means that that the probability that we have is the probability for the success class. Okay, so in this case, it's saying that the probability of this case being a 1 is quite low. It's 0.011, right? And true enough, it's actually a 0. Right? So for example, in this case, it's saying the probability of this case being a 1 is pretty high, 0.903, and we see that it's in fact a 1. Okay, so let's consider this scenario, and we will use this simple scenario to understand the notion of an ROC chart. It so happens that this data set has 10 rows. 5 of them are class 1 and 5 of them are class 0. So we take this original data set, and just for exposition purposes, let's sort it on probability, right? So we've got the high probabilities coming up on top and the lower probabilities at the bottom, and it's arranged in descending order of probability. Okay, so what of course we expect to see is that if the probability is high, then the class is usually 1, right? So with the initial high probabilities, we see indeed that the class is 1, but here we've got some reasonably high probabilities with the class as 0, and we've got a low probability here, but that is still class 1. Of course, we expect that, right? Because after all, these probabilities are just calculated by the model, and you can expect that they are not going to be accurate. And they'll generally be good, but not absolutely perfect. So that is what we expect. As we have seen before, if you apply different cutoffs, right, so you've got the predicted class being different, right? So for example, if I use a cutoff of 0.5, right, then the predictions come out like this, right? The 0, 1, 1, this is a non-sorted thing again. So anything greater than 0.5 or more becomes a 1, otherwise it becomes a 0, and we end up with this error matrix, right? So there are actually 5 ones, out of which 4 of them are predicted correctly if the cutoff is 0.5, and 3 of the zeros are predicted correctly if the cutoff is 0.5. Whereas suppose we use the cutoff of 0, right? So if the cutoff is 0, what does it mean? It means that any probability which is 0 or more will be classified as the positive class, which means every single case will be classified as a positive class, right? So that's what you see here, right? All the ones are predicted correctly as 5. All the zeros are also predicted as 5 because the cutoff is 0. So every single probability is going to be classified as a 1. So that is why you see this kind of error matrix. Right. On the other hand, if we go to the other extreme and make the cutoff as 1, that means in order for something to be predicted as a 1, it has to have a probability of 1. And none of these cases has a probability of 1. All of them are below 1. So every case is going to be classified as a 0, as the negative class. Okay. So that's really what we are seeing here. And clearly, of course, what we want is a trade-off. Okay, so if the cutoff probability is very low, right, that means we have a very low threshold on classifying something as the positive class. So we'll get more true positives. That is, the risk that we will miss something which is actually a positive, in other words, actually a buyer, let's say. Let's say you've got somebody who's a buyer, but for whom the model prediction is a very low probability, right? Then the cutoff may be such that we eliminate that, we miss that buyer. Whereas if you have a very low cutoff, then you will capture more and more of actual buyers, even if their probability is low. But of course, that is going to come at the cost that a lot of people who are not buyers, a lot of negatives, you're also going to classify as positives, right? So if the cutoff is low, you get more true positives, but you also get more false positives. Okay, if a cutoff is medium, then you get false positive and false negative are equally bad, right? And therefore, you will sort of minimize the overall error if the cutoff is like 0.5. Usually with a cutoff of 0.5, you get the minimum overall error, right? But often you're not interested only in the minimum overall error. You're interested in the performance on one of the two classes, usually on the positive class. You're interested in increasing the performance, but you want to trade it off against false positives. Okay, so and if the cutoff goes too high, of course, then you miss out on many true positives. So you don't want that to happen. So clearly you're looking for a trade-off. Okay, so here is a trust partition. Here are the predictor attributes. The target attribute is class. The positive class is 1 as before, and the model calculations are like this. Okay, so the point is, how do we choose the cutoff probability? And as I've said, it's the thing, right? It's the ROC chart that we're going to use to do this. So to bring this whole positive negative discussion all back to a very practical kind of a context, let's go back to our sports car example, right? So on the one extreme, if you want to not miss even a single person who's a prospective buyer, then your choice, of course, is to invite everybody for a test drive. Okay, so if you do that, there is no chance of you missing a real buyer, right? Suppose there's a person who's a buyer. You've invited everybody, so you'll catch that buyer as well. So you don't miss them. But of course, that comes at a steep price, because in order to get that one buyer, you have to process, let's say 25, 30, 50, or even 100 non-buyers. And there's a cost associated with doing that. Okay, so you have a lot of profit that you will earn from getting a buyer, but that profit is going to come at the cost of dealing with a lot of non-buyers, right? On the other hand, you could, of course, avoid the mistake of classifying a non-buyer as a buyer and wasting money on them by not inviting anybody at all to do a test drive, right? So in that case, you have no risk. You're not going to waste your time on somebody who's not a buyer. But of course, that comes at the cost that you're missing on all the buyers too. If you don't invite anybody, how do you expect somebody to come and buy your product? You miss everything. Okay, so clearly what we are looking for is a trade-off, right? Of course, inviting everybody to a test drive is the equivalent of having a cutoff of 0, right? Which means everybody is going to be classified as a buyer. You call everybody. And inviting nobody for a test drive is equivalent to having a cutoff of infinity. Nobody is going to be classified as a buyer, so you don't call anybody. So we are looking for the middle ground here in terms of the cutoff probability.